This video is going to serve as sort of an introduction or reintroduction to volumes. I'm not going to calculate any of the volumes. We're going to simply write the integrals down just in the interest of time. And of course, most of the time you could use your calculator, but I also rely on the fact that we've done a lot of integrals, so you could do the integrals by hand. First thing, just finding the area. Well, of course, area is just integrating 0 to 4. Like that, okay? And maybe just for the general sake of space, I could even just say it's 0 to 4 of f of x dx. Okay? Now, if it were rotated around the axis, find the volume of the resulting solid. Well, if it were rotated, if this were spun around, what we would get are circles. Okay, circular cross sections, because this whole shape would be spun around and we would get circular cross sections. They'd look like, it would just look like a solid. You looked at it head on, it would all be circular. Well, each cross section is a circle. Of course, the area of a circle is pi r squared, and the radius is simply equal to whatever the function's value is. So the area of my circle is pi multiplied by the function squared, and that's what we integrate. Pi, and I like to put my constant multiplier up front. I'm going to put a little bracket around this. So pi r squared. So just notice it's pi r squared. It's just the area of a circle. Okay? Now, if it were rotated around the line y equals -2. Okay, so now, instead of just rotating around the axis, I've got this line down here at -2, and that's what I'm rotating it around. So now, the radius is 2 units bigger. So the radius is 2 units bigger, but here's the one other thing we have to remember. We're taking a shape and we're rotating it around the line y equals 2. So there actually is a hollowed out center that's 2 units, that has a radius of 2 units. So if you think of this thing kind of being rotated around, it would look like a tire or a donut or something, because it's a shape and it's got a bottom and it's rotated around. So we have 2 circles. So we always do the big circle, which would be the function plus 2. And again, the reason we had to add 2 is because rotating around the line y equals -2, the radius is 2 units bigger than it was before, when it was just rotating around the axis. And then we're going to subtract just the radius of the small circle, which was just 2. That. Now you could put this together. They have the same bounds, so you could have just said it was pi times the integral from 0 to 4 of f of x plus 2 squared minus 2 squared, and you wouldn't have needed to write it as 2 integrals. I just wanted to do that here to remind you of how this was working. It was the big volume minus the small volume. Okay. Lastly, let's say we're rotating around the line y equals 6. So now we're rotating around something above it. Okay. So the function, remember, tells us how far off the axis we are. So let me work over here where I haven't written yet. Okay, the function tells me how far away from the axis the curve is. So my radius here is actually equal to 6 minus the function, because my function tells me how far away from the axis the function is. Well, we also have to remember that we're rotating a shape with this bottom, so my big radius this time is just 6. Okay, because I am rotating this whole thing. So again, there's a hollowed out kind of center because this whole shape is being rotated. You know, one way to think about it, it's like two functions where the bottom function just happens to be the axis. Okay. Notice I forgot the dx up here. Let's put dx minus the integral from 0 to 4 of 6 minus f of x squared dx. Okay. So this is how we would find the volume if we're rotating up. The most common mistake is forgetting this number in this example, or this number in this example. Just remember, there is a base to this. It was only the shape from 0 to 4. So just this shape, and when we're rotating it, we got to remember then it will have a hollowed center. And now we're talking about cross sections. Okay, cross sections perpendicular to the x-axis are squares. So you're going to have to forgive my three-dimensional drawing here, but what that means is that we are building squares up off of this. Okay, it's coming up at you off the page, or the computer screen. So the area of a square, okay, the area of a square, of course, is just whatever the base is squared. Well, you notice the base is just the function's value. So to find the volume, we just integrate from 0 to 4. The base squared. Okay. We're always integrating cross sections. So when we do a revolution, like we did on the previous slide, all of the cross sections were squares because it revolved around. Or I'm sorry, they were all circles because it revolved around. But here, the cross sections are squares. Okay. Well, now the next question says there's semicircles. So let me draw one of those. Okay, so now they're coming up like this. Okay. Well, the area of a semicircle is 1/2 pi r squared. So, you know, we go to integrate and we say, well, there's going to be a 1/2 pi out front. It's still going to be 0 to 4. Well, now we need the radius. The problem is, for a lot of people, they look at this and they say, well, okay, the function. Well, but the function doesn't give us the radius, it gives us the diameter. So we have to take our function and divide it by 2. And that is how we're going to get our radius. And a lot of times people look at this and they say, well, this can't be right. I had to divide by 2 twice? Why? Well, it was a semicircle, so it was only half of the area of a circle. And the function didn't tell us the radius, it told us the diameter. So we had to divide by 2 again. So really, we've been given a diameter, a way to find the diameter, and we've been asked to find the area of half a circle. So that's why we had to divide by 2 twice.